Hello and welcome to episode 4 of the SD.RB podcast. Today Tom Werner is going to be talking to us about the power of numbers with Ruby.
Ruby is Awesome Part 1, Numbers. And I know what you're probably thinking. I'm going to talk about numbers for, 20 minutes? There can't be that much to numbers, right? Well, in Ruby, numbers are really quite powerful, and there's a lot of different ways you can use them, and different ways that you can create them, and different ways that they can help you in your programming that you probably don't know about. So we're going to go over some of that. They're a little bit like transformers, and I tried to find a good picture of a transformer, but I figured it'd probably be copyright infringement. So you can use your imaginations. So what I'm going to do is open an IRB session. In the lower left there, can everyone see? Is that too far over for anybody? Looking good? Alright. So in Ruby, you probably know this already. We've all graduated from grade school. But a number in Ruby evaluates to itself. You create a number, and the IRB prompt, if you've not used this before, it's a real-time evaluator for Ruby. Anything you type in here will be evaluated and then printed out the evaluation of that. So if, let's say you're on a Windows machine and you forget where the calculator is, well, you can bust open an IRB prompt and you can do simple little mathematical expressions. You got addition, you got subtraction, you got multiplication, everything works like normal. You can even do parenthetical operations, and those work as expected. Now, you might be wondering why I left out division, and that's because division is kind of like an Apple fanboy. It likes to think different, right? When you divide with integers, you're not going to see the answer that you expect, okay? 5 divided by 2, at least where I come from, isn't 2. Anything that you divide, that's going to produce a number like that. It gets even a little weirder when you start going with negative numbers. Let me do this. Minus 3. So the reason that this is happening is because integers divide without fractions. There's no fractional part of the integer, and so when you divide, it's chopping that off. What it's actually doing is it's taking the calculation and it's flooring it. So 5 divided by 2 is 2.5, floor that 2. 5 divided by minus 2 is minus 2.5, floor that, you get minus 3. So what you want to use is floats for that. A float is like an integer, but it's going to give you the precision that you need. There are no doubles. The doubles that you see in Java are basically floats. There's only one float. It's called float. So if you want to do that computation as you would in the normal world, you use a float, and you do that by creating it with a period basically in the declaration. So 4.0, 0.5, that kind of thing. When you declare it with a period in it, it becomes a float. So the main thing to remember about that is that if you forget that, and eventually you will, and especially for those of you new to Ruby, when you're doing calculations, sometimes you'll freak out because your numbers aren't coming out right, and that might be because you're forgetting to use a float in your operation. And so you might be wondering, when you read a number in from standard in or from a file, well, how do I get that to the kind of thing that I want it to be? So in order to do that, Ruby gives you a couple of different ways. You can take an integer, and if you need to turn that into a float, you can call a method on it called toF that will return the float version of that number, 5.0. And you're able to call methods directly on 5, as it is an object in Ruby, everything is an object, you can call methods directly on it. Inversely, you can take a float and convert it to an integer. Also similarly, you can take a string, for instance, and convert it to an integer. So there's lots of different ways of converting between the different types of numbers, between integers and floats. So now you know a little bit about numbers. We got that out of the way. Let's put them to work for us. I wrote a little program earlier today called float doubling. And when I was about 10 years old, I went to my parents and I said, I have a deal for you. I'm going to have you pay me 1 cent today for doing chores. And then tomorrow, I'm going to reinvest that with you, and I want you to double it. You'll pay me 2 cents the next day. Pretty good deal, right? And the next day, I want you to double that again. I was trying to trick them into something that I think we all tried when we were kids. So I wrote a little program, starting with a payment of 1 cent. I'm going to do this forever, and I'm going to print out, using the puts method, the payment times 2. And this is also going to save the doubling of payment into itself payment. Sure. For debugging, if you're doing like a command line, yeah, you can use puts. If you're doing something that's command line, you can do puts and it'll put it to standard out. It'll print to the console. Yeah. You can also print to standard error. I actually forget the mechanism to do that. There you go, $std error, and you can basically write to that, and it will print a standard error. If you have a way to get that as well, you can send that to an error file or whatever you want to do. But yeah, you can do that using puts, or you can use print. If you look down at the IRB window, just go off on a brief tangent for that. You can put puts, a string, and it returns nil. It'll print 5 to the console, and it'll return nil, which is the return for that method. But you can also call P, which is a similar type thing, but it'll print it out with a denotation of what kind of object it actually is. In this case, it's a string. And you can do print. Puts is basically put string, so it'll add a new line on the end, whereas print will not. As you can see, it's run up on the same line there. So there's a couple different ways that you can print to the console. So back to our float doubling. We got our little program here. But if we run this, looks like we'll be a little bit richer than I thought. No, we got infinity. So what you're seeing here is that floats have a maximum size. Okay, they don't get that big. And what you can actually do is, let's look a little bit into the way the floats are. You can see they turn into infinity after the doubling. Let's look into that a little bit with our IRB here. The float, let's look at it. It's an object, as we know. Well, let's prove that. You can call the class method on a float, 5.0, and you can get what type of thing that is. You can look at the minimum and maximum values for float by getting a constant that's held within that class using the double colon operator. That's a scoping operator. That's how you're going to access a constant inside a class. So floats actually store what their min and max values are. And on here you can see it's 2.2 times 10 to the negative 308 to the positive 308 to 1.79. And you see the E notation on there. That's not just something that you're going to be able to see on output. You're actually going to be able to input numbers like that too. And this is where some of the ways that Ruby works gets kind of interesting. You can actually take a number, like, anybody recognize this number? Exactly. So you can take a scientific number like Avogadro's number, and you can write it. You can actually declare it using E notation, which is kind of cool. It saves you some time when you're writing, so you don't have to, type a bunch of zeros. It's no fun. So similarly, you can go into the negative, and that's going to create a very small number. That's 1 over 6.626 to the times 10 to the 10th 34th. So there's several different ways that you can create numbers. That's one of them. I'll show you a few more later on. One interesting thing to note about the infinities is that you cannot declare an infinite float. You can't go to the command line and create an infinite float. They're only created as the result of a calculation. So if we create a number, say 2e200, that's a perfectly fine float. If we want to take that same number, and we can use the power operator, which is 2 asterisks together, and square it, well, that's too big. That's going to be 2 times 10 to the 400th. That's not going to fly. That's past 300 to the new times 10 to the 308th. But the maximum integer size is, so you get infinity. You can't really do much with infinity, but you can test for it. Using the finite question mark. In Ruby, in case you don't know, some methods actually have question marks on the end of them. It's just another method name. There's nothing special about it. It's usually used to denote that it's going to return a Boolean value. Not always, but generally. So you can test if something's finite. Similarly, show you that if you test an obviously finite number for finite, yes, it is finite. So you can find out if something's finite. Another interesting thing, if you're trying to divide by 0 with integers, you're going to get an error. You can't do that with integers. But you can do that with floats. So if you try to divide 0 by itself, you're going to get another special float. It's not a number. And similarly, you can actually test to see if that's not a number. So there's not a number, and there's infinite on floats. Those are special values. You can't basically declare them, but you can test for them, and they will occur if you get out of the bounds. Good to know. Yeah. I'm not actually sure. I thought if you divide 0 by 0, if you divide a non-zero number, let's try this one. Oops. Yeah, generally if you're going to divide by 0 with a float, you're going to end up with infinity, because asymptotic means approaching. Infinity as it goes, smaller and smaller, closer to 0. So if you divide 0 by 0, you're going to get not a number. If you divide another number by 0 with floats, you're going to get infinity. So now that we know about infinity, let's rewrite this float doubling one with the finite in there. That'll stop it so we don't see a bunch of infinities. So here you go. You can see the progression all the way from 1 cent up to the upper limit of the float. So, interesting thing about floats there. You know, there's some interesting things to be said about floats. They have a range. They have a min and max range. They can be not a number. They can be infinite. So, now you're wondering, if floats can only go so big, what if I need a number that's bigger than that? Well, integers are actually going to help us out there. If we use the same program, only we use integers this time, we use 1, and we'll double it by 2 each time, same as the last one. And we run that, you're going to see that this number is getting very big. And I can sit here, and I can watch this number grow. And I'll actually go on while it's working, so you can see that it's not going to peter out anytime soon. But you can actually create a number as big as your free memory if you allow Ruby to grow that large, which is really cool. And brings us to our next slide, which is not having to worry about big numbers. Big plus in Ruby You just create a number as big as you want. As long as it's an integer, you're good to go. The way it does that is it actually assigns a number of words, memory words, basically, to store the integer. So it's just creating more and more memory space to hold this number, and it strings them together. This will go on forever, basically. But you can see that this number is pretty big. And let's look at what that looks like. Let's look at what kind of classes those are. Your normal integer is going to be of type fixed num. So you see these numbers, these integers are not really of, there is an integer class, and it's basically an ancestor of these classes. The fixed num is basically a fixed number. It's a 4-byte. Your integer, your basic fixed num is 4 bytes, and it contains any of the small numbers that you create. These are all going to be fixed nums. When you start getting big, let's create a big number. You'll see that that's called a big num. So when something becomes too big to be held in a fixed num, it automatically becomes and is converted into a big num by Ruby. You don't have to worry about it at all. Completely automatic. The reason for that is basically, why doesn't it just store everything as a big num? It's for efficiency. Small numbers are passed actually by their value. They're just sent, the actual bytes are sent over, whereas big nums are sent by reference. So you can have as big a number you want. It takes up a gigabyte of memory, and when you pass it to a function, it's passing a reference. So that's the reason for having the two different versions of that. And if you get into writing programs that use numbers in that way, if you're passing them by reference, if you're passing around big nums, you got to watch out for that. I can bite you if you're changing them within your methods, that kind of thing. Got to be careful about that. And another interesting thing is you can actually get the size, and that's going to be the size in bytes of an integer, fixed num or a big num. So 5, a small integer of class fixed num, is 4 bytes. If you look at bigger one, you'll see how many bytes it's actually taking up in memory. Whoops, I'm not supposed to see that. Another interesting thing about numbers, which maybe you knew and maybe you didn't, is that you can actually write them using some interesting methods. I'm going to put some underscores in here, which you think is probably kind of weird. Basically, it's just stripping them out when it creates that, when you're declaring that number. The underscores are a way to separate where you would normally put commas in a number. You can put underscores in them. It's a way for when you're declaring a number to keep track, basically, of where your digits are. You can actually put those anywhere you want in a number. I'm not actually sure if you can put multiples in a row. Let's find out. No, don't put multiples in a row. But you can put single underscores in a number and just strips them out. That's simply for readability when you're coding. Now, this is going to be really cool and something that the Ruby newbie doesn't usually know. But you can actually create hex numbers as you're declaring them. Declare a hex number right in line. So the way you do that is a hex number is prefixed with 0x. Any number that you prefix with 0x is going to be a hex number. You can do that upper or lowercase. You can also declare octal numbers, base 8, by prefixing with a 0. Maybe you didn't know that one. That's one of my favorites. Everyone loves octal. You can do binary numbers, easy enough. And, amazingly, you can do base 10 numbers. So if you ever get tired of being concise, just slap the 0D on the front, I guess is the moral of that one. So you can create numbers in different bases. You can also print them out in different bases using the toS method on the number. This one is going to be on integer. But if you want to get 42 in hex, then you use 2s and you pass it basically a base number, the radix they call it, which 16 hex, 42 of that is 2a. You can get that in basically anything you want from binary up to base 36. I'm not sure if that has a name. Anybody know the name for base 36? Yeah, I didn't think so. But you can go up to 36 and try and do 37. It's going to freak. So don't do that. With the binary, if you think of a number is an integer. It's going to be just a series of bits. You can, let's do this. Let's go back and print this out as binary. So you can see what I'm doing. You can get at the actual bit values in that by using an array notation. That's going to be the lowest order bit on far right, the 0. Index position 1 is going to be 42. It's going to be a 1. So you can get at the bit values in there if you're into doing bit masks. It's a very space efficient way to track things. Some more bit operations that you've seen before. You're going to be able to shift a number by a certain number of bit places. So that's 42 bit shifted to the left 2 places, which is basically 42 times 4, which is 2 squared. Let me show you this. 42.2s binary. We do 42 bit shifted left. That 2s. You'll see that there's 2 extra zeros on the right. It's basically moving the whole thing to the left 2 places, which is basically multiplying it by 2 each place it's shifted. So you can do shift left, you can do shift right, which is division with dropping. That's basically a floored division, just like this is. So that's divided by 4. You're going to get the same answer. That's basically what the integer division is doing. It's shifting to the right. So shift left and shift right with the double greater than or less thans. Another thing that you can do is the OR operator. And this is different than probably the OR that you're going to use in your if statements. This is a single bar, which is a bitwise OR. If we do an OR on 42 and 21, 42 and 21 are actually bit inverses. So you can see that the OR is the inverse. Actually, it's not. I'm sorry, it is. There should be another 0 on the left there. If you see it with another 0 on the left, then you'll see that there's just alternating 0s and 1s, but they're opposite for each number. So when you OR those together, you're going to get 63, which is all of them being 1s. And that's the bitwise OR. So you get that. You can also do similarly a bitwise AND. If we AND those 2 numbers together, you should get 0. It's basically saying if either of them are 1, the result has a 1 in that spot. Simple enough, but you can do lots of bit operations very easily. It's all built-in syntax. And so you can use that notation and those methods to deal with bases. It's probably not something you'd be doing every day, but when you need to do it, it's right there. It's very easy to get to numbers more than meets the eye. You had no idea, did you? Now you do. So let's move on to something that's not quite part of the core, but is still in the core library. You have to require it, which in Ruby requiring pulls in an external library. These are not included by default, but they're easy enough to pull in. Let's look at rationals. We require the rational library. It allows you to create rational numbers, which are basically just fractions. They have a numerator and a denominator. So rational 1, 2, the way you declare it is by just using the syntax, rational 1, 2. And that is basically the fraction 1/2. So if I put If I assign that to a value, and I puts that, you see it's 1/2. So I can multiply that, R1 we have, times itself, and I should get 1/4. So if you're working with fractions a lot and you want to preserve their precision, let's say 2/3, a repeating fraction that goes on forever, and you don't want it to be reduced to a float, then you see the float rounds it after a certain number of spaces, whereas the rational is going to keep it whole for as long as it's a rational object. As soon as you convert it to a float, you can use similar methods, 2i and 2f. That number is going to become an actual float. It no longer has that rational precision. When you create a rational, let's say 5/10, it's going to automatically reduce that for you. If you do not want it to automatically reduce it for you, you can use new exclamation point, and it'll keep it that way. You can then reduce it calling a method, which I believe is reduce, but I don't remember. But it'll keep it as the original if you needed to do that. Use new bang to do that. So, to make rationals not super boring, I know you're all yawning, it's okay. Let's do something interesting. 22/7, what's that an approximation for? Okay, pi. Now, I've always wondered how far away from pi 22/7 is. Seems kind of bogus that something as crappy as 22/7 could actually be a relatively good approximation for pi. So let's create a rational, 22/7, and let's compare it to pi. Let's call it R2, 22/7. And we can get at pi using the math library, constant, math.pi. That's built into Ruby, you get that. It has the precision of a float, so you don't got no 100,000 digits, but it's good enough for most things. And we can compare those two. Put that into a variable called diff, R2 minus math.pi. See what I did there? I used the dot notation. This is a little snafu in Ruby. The dot notation is trying to call a method. Pi is a constant. You have to use it with the scope operator, the double colon, which is why I had that problem there. So here's our difference, 0.001. That's a pretty small difference. Let's see what percentage difference it is. Multiply that by 100. That's the difference. Divide that by pi. Multiply that by 100. And that should be our percentage different from pi. So using rationals, albeit only for a short period, the difference of 22/7 and pi is 0.04%. That's pretty good. So there's another fun fact you learned from Ruby Numbers. Ruby Numbers helped you know that 22/7 actually is a pretty good estimate. So don't feel too shameful if you can't remember pi to 2 digits. It's 22/7. Rational numbers are great. They're fine. But I know what you really want to know about are complex numbers, because none of us use those quite nearly enough. Complex number, you're also going to have to, oops, maybe it's the wrong order. I was actually going to introduce this using the square root function on math. Math has a number of interesting features and methods, one of which is square root. Square root of 25 is 5, it returns a float. The square root of -1 is not a number. Okay. Well, we know that it should be I, which is a complex number, square root of -1. If we include, or require, complex rather, and we math.square root -1, we get a complex number. See, now that's cool. It automatically knows that we included the complex library and is able to produce the correct complex value. So, math.square root of complex 0 and 1.0 right here. In the first part of it, we have the real part, 0, and the complex part, 1.0. So that's I. You can declare a complex number as easily as you can a rational number. And you can multiply those together, doing all sorts of good mathy stuff. 1 squared. You know the drill. Complicated, complex math numbers. I never really liked them either. But you can use them for calculating polynomial solutions. A lot of polynomials will have solutions that are complex that we all just kind of brush off and forget about. But with Ruby, you can get them using the complex library. And another thing, if you want to get the imaginary part of that complex number, you can call the imag method, which is also available as the image method. I think it's easier to pronounce image than imag. But you can actually also call that same function, that same method, on a regular integer, 5. It will give you 0. Complex part of 5 is 0. And the way it's doing this is actually the image method on the integer is actually defined in the numeric class, which is an ancestor of integer. So they added that in there for the guys that are using complex numbers. You can call that on a fixed num or a big num without having to deal with adding another library in there, whatever. That's available no matter what. So, rational and complex numbers, really exciting, probably something you didn't want to hear about. Now you know. I forced you to know. Let's just go over one more quick thing. And that is the math library, which you already saw some of. MathPy. You've also got a good one in there. E, the natural number. Good for all sorts of creating of spirals and all sorts of tools. All your favorite trigonometric functions are in there. If I remember, sine of pi over 2 is 1. So that's correct. It's good to know. Cool one for trig nuts is the hypot method, which will calculate the hypotenuse of a right triangle. So everyone's favorite right triangle, 3, 4, 5 triangle, you can use an hypot. Easy enough. Use that for, I like to use the right triangle for calculating whether or not a room is actually square. So I'm gonna branch off into construction here for a second. But if you have a room and you want to make sure that that room is square, if you're, say, laying a hardwood floor, you can measure 3 feet off one wall, or 6 feet, multiple 3, multiple of 4 off the other wall, 3 off this wall, 4 off this wall, draw the hypotenuse and measure it. If it's 5, or if it's a multiple of 5, if you use the multiple, then your room is square. If it's not 5, then it's not square. And if you have pieces of string to do this with, you can actually figure out what square is, because when you create a 3, 4, 5 triangle, it's square. So I didn't learn that from Ruby, but you did. So use that next time you're checking a room for square. You got some log methods in here. I know we all love logs. Log, and all that. Just to prove that it works correctly. The log of the natural number should be 1. And the log 10 of 10 should be 1. So you've got log 10 you can play with. And finally, there are a few other pieces of Ruby that you can play with if you're so intrigued. Math and matrix and vector are going to be useful for classes like discrete algebra, linear algebra, that kind of stuff. Anyway, math, matrix, vector, XMath is a gem that's available through Ruby Gems that has a bunch of other math methods on it that you can use. If you don't want to write your own, writing math methods, usually part of everyone's fun day. But that basically concludes my presentation on numbers. Awesomer than you thought, I think. And does anybody have any questions? No, clear your minds. It's okay.
That concludes this episode of the SD.RB podcast. See you next time.